Okay, I think we are live. So hi everyone. Let me know if you guys can hear me well. Uh, yes, so welcome to another session. So I believe like we already had started with our L6 session last Friday, but there were some technical issues due to which we had to stop the session. uh, Not last Friday, I believe last Wednesday, because I had my internet was disconnected for some reason, so that's why the stream ended. So I'd already discuss the problems from the previous day, like whatever homework I had given, I had discussed there. So if you like, I don't believe the video is there, but again, like I'm hoping that you had gone through that, like you were there in the live and you have actually gone through those problems, or you've understood like how to solve them. So yeah, like we'll start with today's problem. Today we'll be solving two problems again. uh, the problems will mostly be easy, but again, like there will be homework which will be easy as well, but there will be one difficult question in your homework. Now I could have discussed the difficult question in this class as well, but again, like that's only one application, right? So I don't want to stress a lot on that. It's just that it's a good thing to know. However, I don't believe like it's a very important thing for your interviews. The problem I'm talking about here is finding the kth smallest element in an unsorted array. So you have to do it in order of n time and order of log n space, which actually uses a technique called the median of the medians technique, right? So that actually will make the session more complicated, so I didn't want to discuss that. So I'm giving this for your homework. Whenever you have time, like maybe today, tomorrow, or over the weekend, just try to solve this problem, because again, like you should know everything before, like before you are appearing for your interviews, you should know these things. However, it's not very important from your interview point of view. Again, that's also there, but you should know that, right? So I'll not discuss that today. This will be for your homework, and the technique to use here, like you can just google up about median of medians technique. There are a lot of articles as well as videos around this topic, so you can definitely go through one of them. But in case if you still have doubts, I'll take a class later on where I'll just focus on this problem, and I'll explain how to solve this. But that's like that will be later on, like not today at least. So let me know in the next class, like if you want this problem as well to be discussed, because this will consume a lot of time, like maybe around 1 hour of class. So in case you want me to discuss this, let me know. I'll take a special class on this. Otherwise, this is for your homework. Just try to do it on your end, right? But otherwise, we'll start with today's class. So today we'll be solving the problem. Again, I don't think the description is updated. So just like if you will not get the problem statement, I'll get the description updated. But before, like if you want to access now, just remember, like just write down the problem statements that we'll discuss today somewhere. Like kth smallest element is a homework, right? So just write it down that you have to solve kth smallest element as your homework, right? So just write it down. And the today we'll be solving the two problems: equilibrium point, which is a pretty easy problem, like very easy problem. And after that, we'll be solving the problem peak element, which is also a easy problem, right? So we'll be solving these two problems. uh, so and then I'll discuss about the homework, like what problems we have for homework, right? So just write it down for now, and I'll get the description updated as well. So I think that should not be a problem, right? All right, let's get started, right? So with equilibrium point, let's read the problem statement. So the problem statement tells that you are given an array A of n positive numbers. So you are given an array of n positive numbers. The task is to find the first equilibrium point in the array. Equilibrium point in an array is a position such that the sum of the elements before it is equal to the sum of the elements after it. So you have to find a equilibrium point in the array. What is the equilibrium point? The sum of the elements before so any index in which the sum of the elements before that index is equals to the sum of the elements after that index, that is a equilibrium point. So position sum of the elements is after it. Return the index of the equilibrium point, and you have to follow a one based indexing, right? So for example, 5, right? 5 elements are there: 1, 3, 5, 2, 2. So you have what is the sum of the elements? So let's consider this point, right? So 3 plus 1 is 4, and 2 plus 2 is 4. So the sum of the elements before this index 3 is equals to the sum of the elements after this index 3, right? So this index 3 is a equilibrium point. Similarly, if you have a single element, the single element is a equilibrium point because there is no element before it, there is no element after it. So you have to find equilibrium point, return -1 if no such point exists, right? So that's the and complexity wise, you have to find the order n complexity and order of one space complexity. So this is the problem statement. I'm pretty sure that most of you already have got the solution how to solve this, but let's anyways discuss this, right? Just give me a second. Okay. So okay. So what do we want? We want to find an index such that sum of the elements before that index is equals to the sum of the elements after that index. So let's say our index is I, right? Our index is I, which is a equilibrium point. So the sum of the elements before this index I should be equals to sum of the elements after. Yes, prefix sum. That's definitely true. So what you can do is you can create the base. So you can have the prefix sum, right? So for any index I, what is the sum of the elements before I? It will be prefix sum of I minus 1. And what will be the sum of the elements after index I? That will be basically prefix sum of n minus 1 minus prefix sum of I. So this is the condition that has to be satisfied. Prefix sum of I minus 1 is equals to prefix sum of n minus 1 minus prefix sum of I. Why n minus 1 minus I? So you are what is prefix sum of n minus 1? It is sum of all the elements, right? From that you want the sum from I plus 1 because I is you want all the elements after I. So I plus 1 to n minus 1. So you have to subtract prefix sum of I from that. So you get the sum of I plus 1 to n minus 1. Yes. So this is order of n space complexity, right? That's true. That's true. So how can we modify this? It's actually pretty simple. The modification as well is pretty simple. So let's actually understand, what do we actually need prefix sum? Do we actually need to compute the prefix sum separately? What if we maintain a running sum, right? What if we maintain a running sum? Let's say sum is a variable. We are at index I. What does sum store? Sum stores all the sum of the elements from 0 to I minus 1. When we are at index I, sum stores the sum of the elements from 0 to I minus 1, right? So what will be the sum before this? Sum before I, it will be sum. What will be the sum of the elements after I? It will be the total sum of the array minus sum minus A of I. You just have to subtract sum will subtract all these elements. A of I will subtract this element. So you have the sum from I plus 1 to n minus 1, right? So what we can do is we can maintain a running sum. So let's actually understand this, like what do I mean by running sum? Okay, I think it's pretty simple, right? You must have got this, but again let's understand. So 1 3 5 2 2. Okay, what is the total sum? First let's calculate the total sum. Total sum is equals to 3 plus 1 4, 4 plus 4 8, 8 plus 5 13, right? So we'll maintain a sum initially to be 0. We'll start up at first index. So now if you see, what is the sum of the elements before the first index? It is 0 pointed by sum. What is the sum of the elements after the first index? That is total sum minus 0 minus A of I, that is 1. So 12. So is 0 equals to 12? No, right? So we will continue. This is not an equilibrium point. Okay. Now when we continue, we add 1 to our answer, to our sum, right? Sum becomes 1. Now we have 3 here. What is the sum of the elements before C? 1, 3, 1. That is in sum. What is sum of elements after 3? That is 13 minus sum, that is 1, minus A of I, that is 3. 9. So is 9 equals to 1? No, right? So we will add 3 to this, so it will become 4, and we will skip. We'll go ahead, right? Okay. What is the sum of the elements before 5? It is 4, right? So 4 is the sum of the elements. What is the sum of the elements after 5? That is given by total sum 13 minus sum, that is 4, minus A of I, that is 5. So 13 minus 9, that is 4. So is 4 equals to 4? Yes. So we will return that this index, that is 3, is the equilibrium point. So this is the logic. Does this make sense? Anyone has any doubts with this logic? How can we do this? We can quickly write the code for this. So we will maintain a long total equals to 0, and also long sum equals to 0, right? So first let's calculate the total sum for int I equals to 0, I less than n, I plus plus, total plus equals to a of I. Now for what we'll do here, for int I equals to 0, I less than n, I plus plus, int remaining like right sum. So let's call it right sum. Right sum is what? Is the total sum minus the sum minus a of I. So if right sum is equals to sum, then return I plus 1, otherwise return minus 1, right? But for calculate total, yes, the time complexity is order of n, right? So the time complexity we have to do in order of n time. The space complexity is order of 1, right? It's just two variables that we are using. Okay, we got a minus 1 somehow. Total sum plus equals to a of I. Okay, I equals to 0, I less than n, I plus plus. Right sum equals to total minus sum, the sum that we have, minus a of I. Right sum I plus 1, and sum plus equals to a of I, that we have to do, right? So submit. So this time space complexity is order of 1, time complexity is order of n, which is expected, right? The expected complexity. So this is, I think this was pretty simple, and I'm pretty sure that you understood this. So let me know if you didn't understand something. I'll repeat again. Let's go to the next. Right, yes. So you did. Let's go to the next problem, that is peak element, right? So let's read the problem statement. An element is called a peak element if its value is not smaller than the value of its adjacent elements, right? So you are given an array ARR of size n. Find the index of any one of its peak elements. The generated output will always be 1 if the index that you return is correct, otherwise the output will be 0. Okay, so what we have to do is we have to return the index of peak element. Right, now this problem actually, as per the complexity, right, as per the complexity, the problem statement is a bit wrong. What it means here is that the array will be a bitonic array, right? It will be increasing, after that it will be decreasing. It didn't mention that. It is like it treats it as a general array. In a general array we can have multiple peak elements, right? So in that case we have to go for order of n complexity. There is no way we can do it in order of log n. But as this is but as the complexity asked here is order of log n, so we have to assume that the problem is basically you are given an array where it's a bitonic array, right? What do I mean by a bitonic array? A bitonic array is basically, it will be increasing first and decreasing, right? Something like that. So it will be increasing first and then it will be decreasing. So we have the array like this, increasing first and decreasing. Okay, it has, 1 second. Okay. It is increasing first and then decreasing. So we have to find this one, right? The peak element. We have to find this peak element. That is the question, right? So let's take an look at the input. So 1, 2, 3. So here 3 is the peak element, right? 3 is the peak element. So it can be increasing and decreasing as well, or it will be a bitonic. 3, 4, 4 is the peak element, right? So 4 is the peak element in this case. So in a general case, like in both the cases, we are given an increasing array, but in a general case, it will be something like this. It will be increasing first and after that it will be decreasing. So you have to find the peak element, right? Let's understand this with an example. So let's say you are given an array like this, 1, 2, 5, 4, 3. So this is, what is the peak element here? 5, right? 5 is the peak element here. So you have to locate this 5. What is the index where 5 is occurring? That is the peak element is occurring. So this is the question that is given to us. How can we do this, right? How can we do this? So the straightforward solution is just running a loop, right? You will just run a loop and you will check for every element whether it is greater than the surrounding elements, right? Whether 2 is greater than 1 and 2 is greater than 5. No, right? So so you will go to the next element, 5. Whether 5 is greater than 2, 5 is greater than 4. Yes. So 5 is returned as the peak element. So we'll go through all the elements one by one. We'll check if the element is greater than the previous element and greater than the next element. In that case, we'll return that element as a peak element. So that will be a order of n time complexity, order of 1 space complexity, right? So, but again, like we want to do it in a better way. So let's understand how we can do it in a better way, right? Okay. So one property, like we will do a, like whenever you see the complexity, right? Whenever you look into the complexity is what? It is log n, right? The complexity is log n. That actually hints us, like whenever you have an array and you have to find something in logarithmic time, it definitely hints us towards the binary search solution, right? It definitely hints us towards the binary search solution that we might have to do some kind of binary search. But here we actually have a problem. The array is not decreasing, the array is not increasing, right? How can we do a binary search then? That's the question, right? So why do we need the array to be increasing or decreasing? First, let's understand that whenever we are doing a binary search, why do we need the array to be increasing or decreasing? That is because when we make a comparison, right, we always want to discard half of the search space. Like let's say this is the initial first iteration, this is the search space. In the second iteration, we find something mid and we check the value and we discard half of the search space and our search space reduces to the first half. So for making this comparison, we need the array to be in a monotonic fashion so that we can discard half of the search space every time, right? So definitely the array is not monotonic, right? The array is increasing and then decreasing. So it is definitely not monotonic. But actually there is a property in the array which is monotonic. What is the property? If you look into the first half, right? If you look into the first half, you can see that the elements are increasing. That is, if you compare a of I and a of I plus 1 in the first half, a of I will be less than a of I plus 1. So let's consider this to be a 0. In the second half, if you see a of I and a of I plus 1, you will see that a of I is greater than a of I plus 1. So let's consider this to be a 1. So if you look into this array carefully, the array is something like initially it is 0. At some point it becomes 1. A of I and I plus 1, and it will remain 1 after that. So what is our goal? Our goal is to find this first occurrence of 1, right? Now with this property, it actually becomes monotonic because we can discard half of the search space by using this check whether a of I is less than a of I plus 1 or a of I is greater than a of I plus 1, right? So this basically, so it is not always when you are given a binary search solution, right, problem, right, it is not always that you will be given the array in a monotonic fashion. The array might not be monotonic, but there is a property that will be monotonic, right? There is a property that will be monotonic. You just have to identify that property and see if that property is actually monotonic. So in this case, this check a of I less than a of I plus 1, it actually is monotonic, right? So or we can consider, like we can consider it in terms of a function like predicate function p of I is if a of I is greater than a of I plus 1, right? In that case, we will have a false and then true types of array, and we have to find the first occurrence of true, right? That's the question. All right. So now it is pretty simple, right? Now it is pretty simple. Let's actually quickly dry run on our test case. We'll create a test case, a big one, and we'll try to dry run. Um, 1, 2, 3, 7, 6, 5, 4, something like this, right? So what is beginning? Beginning is this one, end is this one, right? Let's say this is the mid. Mid will be 1, 2, 3, 4, 5, 6, 7. 7 elements are there. So 1, 2, 3, 3. This one will be the mid, right? In the mid, we'll see, is mid greater than mid plus 1? It is true, right? Mid is greater than mid plus 1. So that means the answer that we have, that will definitely lie on the right hand side, or that will definitely lie on the left hand side, right? Because we know that the decreasing trend has started. The decreasing trend has started, so it is in the second half. The decreasing trend has started, so it is in the second half, right? So we can, what we'll do end is equals to mid. Now what is the mid here? Now mid will be, this one will be the mid, this one will be the mid. So now we'll check a of mid and a of mid plus 1. Is a of mid greater than mid plus 1? No, right? So definitely the answer is towards the left hand side, towards the right hand side. So we will mark the beginning to point to this. We will mark the beginning to point to this. Now we'll again check mid, this one. Is a of mid greater than a of mid plus 1? No, right? So the answer is definitely to the right side. So we will make the beginning point to mid. We will again check here, is a of mid, right? If a of mid, what is mid here? Mid will be again this one, right? Now we will end, like whenever we reach this condition, see, after this the mid will always be here, so it will always be false, so we'll run into an infinite loop. But basically, where have we ended? We have actually ended in the, so if we consider the array to be zeros and ones, just see where have we ended. 0, 1, 1, 1, 1. We have ended at this point, right, where low points to this 0, high points to this 1. So that is, we can end here and we can tell that high is the answer for us, or end is the answer for us, right? We can tell that. So this is how we can binary search and quickly reach to the peak element. Does this make sense? We can try writing the code for this, but let me know if this makes sense. Like, is the solution clear? So is the solution clear? Low equals to 0, high equals to n minus 1. Okay, low equals to 0, high equals to n minus 1. Now, if all the elements are equal, right? If all the elements are equal, so what can we do? In that case, we have to return the first element. So that is one of the cases, right? The corner cases will be the array is decreasing, the array is increasing, and all the elements are equal. Those will be the corner cases. Okay. For the first case, like if all the elements are equal, we can maintain a flag, bold flag equals to false. For int I equals to 0, I less than n minus 1, I plus plus. If ARR of I is not equals to ARR of I plus 1. If there is a difference, we'll set the flag to true. Right. Sometimes we have to write L less than, sometimes R less than equal to. Can you please help? L less than equal to R. Yes. So it depends on how you are writing the binary search, right? It depends on how you are writing the binary search. So generally, when in some cases you are true, exactly true. Like when you are finding an element, generally it's again a general notion, right? It's how you're writing the binary search, how you're how you're writing the binary search. How I prefer writing it as like my logic generally is so there are two problems, right? When you are searching for an element, right? When you are searching for an element, generally you write the normal variant of binary search, and in that case it will be low less than equal to high, right? And low equals to, in that case you assign low equals to mid plus 1, high equals to mid minus 1, like this. So it makes sense to be low less than equal to high. But when in other cases, it depends on how you're writing the binary search. How I generally prefer, like, what is the array that we have? The array is eventually something like 0 0 0 0 1 1 1, like this, right? So I always prefer keeping my low to a 0. I always prefer keeping my high to a 1. my low will always point to a 0, my high will always point to a 1. So where do I end? I will always end at this position, because if my low will always point to a 0, high will always point to a 1. So I'll always end at this position. So my condition here will be low less than high minus 1. That is what I have to make sure, right? But it again depends on your implementation. If you are not doing it like that way, so you can your implementation wise, you have to like make the condition, right? So just think about how it will end up, and in that way you have to make the condition, right? So if flag, if not flag, so in that case return ARR 0. Okay, now we will make a check here, boolean bull check. It will take the array, right? Bull check, it will take the array. Now we have to check the array is increasing as well. That is something that we have to check. If the array is increasing, right? If the array is increasing, so again, like here flag is true, right? So let's set the flag to be false again, and let's check if it is increasing. For int I equals to 0, I less than n minus 1, I plus plus. If ARR I is greater than ARR I plus 1, if it is not increasing, then we will set the flag equals to true, right? Now if it is increasing, if flag not, if it is increasing, that is if it is not flagged, then return ARR last element n minus 1, right? That's done. Now what we have to do, we have to create a check function, right? Int check int ARR int ARR int I, int check int ARR int I. You have to check if ARR I, what is the check that you have to do in the second half? What happens? ARR I is greater than I plus 1, right? So if ARR I is greater than ARR I plus 1, you have to return true, or you can do return ARR I greater than ARR I plus 1. Return ARR I is greater than ARR I plus 1. Then the second half, this is there, right? Okay. Oh, right. It will give a order of NTC, right? We are actually running a loop. Yeah, but I think we can do something here. What can we do? Let's think about this. So there will not be equal, like if there are equal elements, right? So we can just check if there are equal elements. So ARR 0 equals to ARR 1, because otherwise it has to be distinct elements, right? Because otherwise our check that we are doing greater than or less than, that will not be valid. So either it will be, there will be no equal as in the two consecutive elements will not be equal, or two consecutive elements will be equal. So ARR 0 is equals to ARR 1, so we'll return in that case we'll return ARR 0, right? We'll just assume that everything is equal, right? I think distinct element should have been given here. I'm not sure if distinct element is the condition that is given here. Peak element, no, it is not given. So we have to assume that it might be equal, right? So that's one case. The second case will be what? The second case will be last one, right? It is a complete increasing array, but I feel we can definitely tackle the increasing part. We can tackle the increasing part like just we can always return true if the last, like for the last element, right? So int n, we'll also take n here. Now we'll always check if n I equals to n minus 1, we'll always return true in that case. I equals to n minus 1 will return true, just return a true in this case, right? So it will just return a true in this case. Now the first thing that we'll do, if the array is decreasing, right? So if check of low ARR low n, if low is true, in that case we have, it is a decreasing array, so we have to return ARR 0 again. Otherwise, while low less than high minus 1, right? While low less than high minus 1, int mid equals to low plus high by 2. If check of ARR mid n, if it is true, in that case high will be equals to mid, right? Else low equals to mid, and we have to return ARR high. I hope that this actually works. I'm not sure, but let's see if this works. So Let's run this. I'm just skeptical about the corner cases here. Okay, first output 1 2 3. In that case, somehow it didn't. We can just return 1 2 3, right? Oh, okay. Our last element check is also easy, right? If what we can do is, if ARR n minus 1 is greater than ARR n minus 2, simple check, right? In that case, we'll return ARR n minus 1. And also one more thing that we can do, we can make sure that if the array is size 1, right? If n equals to 1, if n equals to 1, we can just return ARR 0. So that brings us only n greater than equal to 2. So then I think this check comes is satisfied. So let's run this. Why are we still getting a 0? What do we have to do? We have to return an index or what? If the index, okay, you have to index, return the index, output 2 0 1 2. Okay, we have to return the index, right? So here we have to return 0. We have to return 0. We have to return 0. We have to return n minus 1. We have to return 5. Okay, I think that should do. So let's submit. Okay, it's done. So yeah, that's the solution, right? So basically what I'm doing here, firstly, we are getting rid of all the corner cases, right? So first is, if there is one element, just return the first index. That's the P. After that, what we are doing here is we are checking now if all the elements are equal, right? If all the elements are equal. Now, if you think about it very carefully, when you are given this constant, although the problem statement is not clear, but as the constant is given log n time, if you think about it very carefully, if there are equal elements, right, it is impossible for you to detect whether to go left and right. Like if two consecutive elements are equal, so it should always be going up and going down in case of a bitonic. Otherwise it will be an increasing, decreasing, or equal array, right? So just check two consecutive elements, ARR 0 and 1. If they two are equal, if these two are equal, then you can just return 0, because all the elements, you can assume that all the elements will be equal. Otherwise, here basically check ARR low. This is not needed. You can also do like this, that if ARR 0 is greater than ARR 1, that means what? That means that the first element is greater than the second element. That means it is a decreasing array. It is a decreasing array altogether. So in that case, the greatest element will be what? ARR 0. So you will return 0. Otherwise, if it is an increasing array, that is ARR n minus 1 is greater than ARR n minus 2, then it is an increasing array. So we return n minus 1. Otherwise, what we do the binary search now. That is, it is a valid bitonic array. It is increasing, after that decreasing. So the low points to a false, high points to a true. Now, what is the check that we are doing? The check that we have done here is ARR I is greater than ARR I plus 1. So that is like, if ARR I is greater than I plus 1, then return a true, otherwise return a false. Right? So actually we can dry run for a test case. Let's dry run on a test case, right? Okay, I think the corner cases are self-explanatory. I don't need to explain, but again, like this one, all elements are equal, right? Like if the array is like 1 1 1 1 1, something like this, so in that case, this is the condition where it will fall, right? So we'll return that. The second part, ARR 0, ARR 0 is greater than ARR 1. In that case, what is the condition? So the condition, the first element is greater than the second element. So that means it will be like 4 3 2 1, something like this, right? The array. So the first element will be the peak element. So we return a 0 here. That's the second case. The third case will be ARR n minus 1 is greater than ARR n minus 2. That means this case will be what? 1 2 3 4. ARR n minus 1 is greater than n minus 2. So it is an increasing array. So the last element should be the peak element. That's what we have written. Return n minus 1. Otherwise, while low less than high minus 1, right? So let's take a good example here. So let's say the example is something like this, that 1 2 3 4 7 6 5, something like this. So 7 is the peak element. So we start off at low. Low is this one. high is this one. Okay, let's take 1121. 1121 will not be possible, right? 1121 will not be possible because if you have two consecutive elements to be equal, right? If you have two consecutive, actually, if you have three consecutive elements, in two also you can decide based on I minus 1, I and I plus 1, you can decide on these three things. But if three consecutive elements are equal, in that case, you can never decide, right, which way to move. So you cannot use a binary search solution. So as the complexity suggests the binary search, so that's why we have to assume that either the element will be all equal, or it will be decreasing or increasing, or it will be increasing first, decreasing. Increasing means strictly increasing, strictly decreasing, right? Not equal elements. So we will have the cases like this only. 1121 will not be there. Okay, so mid and just think about, like, if you want to think about a binary search solution, when two consecutive we can tackle, right? We can anyways tackle, like we can compare mid minus 1, sorry, mid minus 1 and mid plus 1. We can compare these three things, right? So based on these three things, we can definitely judge like what is the path that we want to go. But if there are three, all these are equal, then which way will you go? How can you make a decision there? You cannot make a decision to make a move, right? So binary search you cannot do. Okay, low high 1 2 3 4 7 6 5. Mid will be 1 2 3 4 5 6 7. I think this one will be the mid. Okay, let's see. ARR mid. Now we check mid equals to low plus high by 2. This is the mid. Check ARR mid n. So what is the check? ARR mid is greater than ARR mid plus 1. So ARR mid is greater than ARR mid plus 1. No, right? So in that case, it is false. So low equals to mid. So our low will move to this 4. Now what is the mid? 7. This one. Mid. Right? So now again we check. ARR mid is greater than ARR mid plus 1. This is the check that we are doing. ARR mid greater than ARR mid plus 1. So this satisfied. So we'll do high equals to mid. So our high comes here. Now see, low less than high minus 1 is false, right? Low less than high minus 1 is false. So we return from here and we return high. High is indeed the peak element, right? High is indeed the peak element. So that is how we are getting. So I have modeled this question into this format, that I've used a predicate function here. So I'm using a predicate function here. The predicate function is if so P of I is if ARR of I is greater than ARR of I plus 1. So I see that the array, resultant array will be, initially it will be false. At some point it will reach the peak and it will become true after this, right? So we want the first true. So where do we end at? We will always make the low point to a false, high point to a true. So we will always end in this point, right? So low will point here, high will point here. So that is what we were pointing at, and this is the answer to our solution. Does this make sense? Does this make sense? Okay, good. So yeah, again, like this will be your homework. It's a medium problem. You have to find the kth smallest element. Now the technique that you have to use here, I've already told, that median of medians. Just learn about that and see if you can get that. Otherwise, if you are not able to understand, I'll take a different class like for explaining this, right? So this will be one of your homework. Just note these things down because I don't think it is added in the description. The second is very easy problem. It is, you are given an array of n elements. You have to find the minimum index based distance between two elements of the array. So you have to find the minimum index based distance between two elements. It's a basic problem. It's pretty simple. The third question, that is also a medium problem. We are given an array A of size n and the integer x. Find if there is a triplet in the array which sums up to the given integer x. So you have to find if there is a triplet that sums up to x. The complexity that is expected is order of n square. right? So I think that it is also pretty simple. So what you have to do, you have to find if there is a triplet that sums up to x, right? So these are the three questions that you have to do. All right. Yeah. So these are the three questions that you have to do. Note them down. Triplet sum in array, minimum distance between two numbers, and kth smallest element, right? So try solving this. If you're not able to solve kth smallest element, I'll discuss this in a separate class altogether. But again, like, just try to understand what is median of medians. There are a lot of videos around that. So try to do that on your end. Again, like, as this is not very important from interview point of view, that's why I'm not very keen on explaining. But again, like, if you need that, I'll definitely do that. So let me know in the next class, like, do you want a session on this or not? Other than that, yeah, try to complete these homeworks as well. Pretty simple questions, but try to complete them. All right. Okay, so I'll be meeting you guys in the next class then. Thank you guys for joining in. I hope that you don't have any doubts. So yeah, I'll be meeting you in the next class. Let me see if there's any question.